All right, the practice question today is about rates of change. We got a camera exactly 1 mile from a space shuttle launch site. It's tracking the ascent of the spacecraft for a network news program. At what rate is the camera angle of elevation increasing in order to maintain its focus on the shuttle 30 seconds into the launch? Once the shuttle has reached a height of 9,720 feet and is traveling 700 feet per second. We want to report our answer in radians per second, accurate to 4 decimal places. They give us a little hint here. Again, AP is a US based, and you're going to get a lot of imperial measurements. So this one is 1 mile is 5,280 feet. All right, I'm going to start like most questions. Let's get a visual of this. So we have our camera over here on the ground, and we are watching our space shuttle launch into the air. Okay, so here's our space shuttle launching into the air. Okay, we are 1 mile or 5,280 feet away from the launch pad. There was our launch pad here. And at this point in time, let's call that D. At this point in time, we are taking our snapshot here, and our height is 9,720 feet. And it is traveling at 700 feet per second. So as a rate of change of height is 700 feet per second. Now this angle, there's theta, he's going to steadily have to increase that angle to track the space shuttle. So there's theta, and we want to find d theta dt. All right, so this is what we're given and what we want to find. Okay, so let's go ahead and attack this question here. All right, so I'm going to slide this up so we can really just see our picture. All right, I need a relationship that includes theta and our other two pieces of information. So for this particular question, I'm going to use some trig. So I'm thinking tan theta is equal to opposite over adjacent, so that is height over distance. Now, for this particular question, we want the rate of change, so I'm going to have to find the derivative of this expression. Now, we're going to use some implicit differentiation. We're going to find the derivative of this with respect to time. So now I'm going to take the derivative of tan secant squared theta. It's not time, so we put in our d theta dt. On the right hand side, we have quotient rule, so I'm thinking d h dt, because the derivative of h is 1 dh dt times the bottom plus, that's not right, minus the top times the derivative of the bottom, which would be dd dt, all over the bottom squared. Now we got a few things that we can get rid of here. The distance from the launch pad is not changing. So in fact, dt, that's just a big zero. So that is all gone. We can also do a little canceling right here. So now we have our expression that we're going to solve for d theta dt. So I'm going to rearrange just one more time, and I'm going to get d theta dt is equal to dh dt. Now, secant squared is actually 1 over cosine squared theta. So I'm going to multiply and get dh dt times cosine squared theta, and the whole thing is over d. So this is the question, or this is the formula that I need to go ahead and solve. So at this point we want to look to substitute. So let's scroll this up. I'm going to substitute in some stuff here. I don't know the d theta dt. That's what I'm trying to solve for. But dh dt, that's the rate of change of height. So if we look back or think back, that was 700 feet per second. We have cosine squared theta. I don't have that theta at this instant in time. So I'm going to go ahead and I'm going to find that. But I'm just going to finish this off. D was our 1 mile, 5,280 feet. All right, so I'm going to need this theta right here. At this instant in time, what is theta? Well, let's think about that original equation that we started to work with here. Tan theta was our h over d. Well, our h at this instant, 9,720 feet, and d was 5,280 feet. So if I do a little switch, I can take tan inverse of all of that expression. I'm just going to think we're moving that down. Tan inverse of that will give me theta. So I'm going to my calculator here, and I'm not going to show this. You guys know how to use your calculator now, though. But I'm going tan inverse of 7,280 9,720 divided by 5,280. And I'm making sure, please, we're in radians. So we got to make sure that we're in radians. So theta is 1.073181, and it does just keep going. So I'm going to take all of this, and we're going to put it in there. So let's go ahead and solve my equation for d theta. 700 times cosine 1.07. Now, a lot of times we just want to go second function answer. It'll put that answer in our question, or try to keep as many decimal places as we can here. And remember that cosine is squared. We want to square all of that. And we're going to divide that by 5,280. And when we're all done, d theta dt, let me just slide this up one more time. D theta dt is 0.0302. There's 4 decimal places. 0302 radians per second. Okay.